The first topic we're going to be looking at in the Module 1 Mastery assignment is integration by parts. Integration by parts undoes the product rule of derivatives and allows us to integrate the product of two functions. The product rule of derivatives is just a method for differentiating the product of two or more functions. The formula for integration by parts is u times v, minus the integral of v times du. Remember that integrals calculate the area under a curve, and integrals also undo derivatives. The first problem we're going to be looking at is the integral of x squared times sine 4x dx. This x squared times sine 4x dx is our integrand. And integrand just means the expression that is going to be integrated. The first step for solving this problem is determining your u and dv values. Your u value should be easy to differentiate, while your dv value should be easy to integrate. For this problem, I chose x squared for the u value because it differentiates to 2x, and then you have your dx. The dv value I chose was sine 4x because it integrates to negative cosine 4x over 4. The second step to this problem is to plug your values into the formula. Doing this gives you negative x squared times cosine 4x over 4 minus the integral of negative cosine 4x over 4 times 2x dx. This simplifies to negative 1/4 x squared times cosine 4x plus 1/2 times the integral of x times cosine 4x dx. Notice that this integral also has two terms being multiplied by each other, so we need to do a second iteration of integration by parts. The third step to solving this problem is to do your second iteration of the integration by parts. So we're trying to integrate the x times cosine 4x dx, and so we need to find our u and dv values. The u value I chose was x because it differentiates to 1, which just leaves us with dx. And the dv value I chose was cosine 4x because that integrates to sine 4x over 4. When you plug these values into the formula, you get x times sine 4x over 4 minus 1/4 times the integral of sine 4x dx. The fourth and final step to this problem is to combine both iterations. This first clump, the negative 1/4 x squared times cosine 4x plus 1/2, is the first iteration of our integration by parts. This clump in the brackets is the second iteration, and the second iteration is equivalent to the integral we got after doing our first iteration that was originally multiplied by 1/2. When we simplify all of this, we get our answer, which is 1/4 x squared times cosine 4x plus 1/8 x times sine 4x plus 1/32 times cosine 4x plus c. The second topic we're going to be talking about is improper integrals. An integral is improper when the a value or the b value is equal to infinity. It's also improper when the region defined by f of x has an indefinite discontinuity. When the a or b is equal to infinity, that is a type 1 improper integral. And this a and b that you see are the limits of integration, which is just the domain values that bound the integral. And when the integral has a region defined by f of x that has an infinite discontinuity, that's a type 2 improper integral. And discontinuity is just a place where the graph has a break. So that can be caused by a hole, a jump, or a vertical asymptote. The problem we're going to be looking at is the integral from 1 to infinity of 1 over x squared dx. This is a type 1 integral because the b equals infinity. To solve this, we're going to have to take the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. The infinity gets turned into the t that's approaching infinity. and the limit. This will make more sense on the next slide. Our first step is to set up the limit. So we have a limit at infinity, the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. The infinity, like I said before, was replaced by this t because right here we have the t approaching infinity. The second step is the first step to solving the integral using the FTC. So when we do this, we need to solve the indefinite integral. So we have the indefinite integral of 1 over x squared, which equals negative 1 over x. The third step to solving the problem is to plug this back into the limits and use the FTC to solve the definite integral. Now, the FTC is the fundamental theorem of calculus, and it states that an integral from a to b of f of x dx is equal to big F of b minus big F of a. So that means you find the indefinite integral of f of x dx, and then you plug in your b value into the function, and then you subtract that by the a value plugged into the function. When we plug this back into the limit, we get the limit as t approaches infinity of negative 1 over x from 1 to t, which when we plug in the t and the 1 and subtract it, we get the limit as t approaches infinity of negative 1 over t minus negative 1. The fourth and final step is to solve for the limit. So again, we have the limit as t approaches infinity of negative 1 over t plus 1 because we had the minus 1. And we can break this up to the limit as t approaches infinity of negative 1 over t plus the limit as t approaches infinity of 1. When you solve for this first limit, you get 0. And when you solve for this second limit, you get 1. And when you add those two terms, you're left with 1. So we know that this problem, this integral, converges at 1. We would be able to tell if it was a divergent integral if one of these limits gave us either a negative infinity or a positive infinity as an output. And we would know immediately that it was divergent. A divergent interval is divergent improper integral is just an integral that does not have a defined value since the limit we set up to find it does not exist. And a convergent improper integral is an integral that has a defined value that's found through this limit taking process that we just did.